Start, Aisha.
Hello, everyone. My name is Aisha, and I'm a first-year PhD student at the Paris Observatory, working with Jeremie Vaubaillon. And today, my talk is going to be about meteor showers. Is it connected? Okay. No, okay, now it works. Yes, okay, perfect. So, and this immediately raises a question if all of these cases represent genuinely real physical streams. And before we get into that, let's talk about what makes a shower a shower. And recently, the IU MDC working group has developed a stronger criteria for a shower to obtain the status of an established one. And it consists of 3 obligatory points. And I want to focus your attention on the second one that requires each solution to be identified using at least 15 members of the shower. And if we check this criterion for the existing list of showers, we get this image and we see a clear difference between all showers and the subset of established ones. So the established ones tend to be composed of way more meteors, between hundreds and thousands, and so they're quite abundant. And in contrast, majority of the showers are relatively weak, peaking between 10 to 20 meteors, which is not so far from the lower limit threshold value of 15 meteors. And as for the next criteria, it requires showers' existence to be supported by an evaluation of its statistical significance with respect to the local sporadic background or estimations of the probabilities of random coincidences. And this one's very important, but unfortunately, many of the showers do not provide information on this. So it's hard to tell which cases have even done any statistical tests. So looking at just these criteria, we already see some flaws. And there is also another criteria that is not obligatory, but would definitely strengthen the position of the shower candidate, and that is that the parent body of the stream is known or there's a candidate for it. And if we have a look at this situation, then out of all the showers, only 188 have some sort of information on their parent bodies, and only 44 of those are related to established showers. And even then, out of all these parent bodies, most of them are candidates that have not been definitively proven. And if we take a look at the origin of these showers, we see that the cometary origin is more common among established ones. And in a sense, well, with respect to the asteroidal origin, and in a sense, it aligns with our better And now if we overlay the mean orbital elements of our showers, and it doesn't work again. If you can go to the next slide. Okay.
Sorry, technical difficulties. Yes, Zoom crashed. So yes, sorry, Aisha,
Right.
because I guess we are not be broadcasting. Now we should be broadcasting again. Okay, you can continue.
So if we overlay the mean orbital elements of our showers, both established and working list showers, we see several showers to appear in the regions where we have not identified parent body sources yet. So that is yet another discrepancy. So all of this brings us back to the question of how many of these cases represent real physical streams, because if we were to claim all of these showers to be true, then wouldn't we be observing more parent bodies or parent body sources? And as we've seen, that is not really the case. And on the other hand, if a large fraction of these showers turn out to be false, for example, arising from like statistical coincidences or classification issues, which I believe will be covered in the next talk. Then we have a methodological problem, and we need to refine the way we detect, define, and classify meteor showers to ensure that only true streams make it to the database. And so the first question we ask ourselves is it even physically and dynamically plausible to have 1,000 meteor showers, given our current understanding of the solar system, especially the near-Earth objects? And to answer this question, we consider 3 key sources. So comets that are on near-Earth and Earth-crossing orbits, near-Earth asteroids, and especially among them active asteroids that exhibit comet-like behavior. And in a sense, by investigating how these behave and might generate meteoroid streams over time, we aim to assess if they can account for such a large number of meteor showers. And so for the remaining part of my talk, I'm going to focus on comets as a source of meteor showers from a dynamical perspective. And so during its dynamical evolution, a comet's orbit can significantly change due to gravitational perturbations. And a key mechanism here is the quasi-Lidov cycle that basically leads to periodic exchanges between the orbit's eccentricity and inclination. And these oscillations have a quite neat consequence for meteor showers, because each time a comet's node and perihelion shift, it can shed light into different orbital planes. And therefore, during its whole quasi-cycle, one comet has the potential to produce multiple distinct meteoroid streams, and hence multiple distinct observable showers. And so although all the comets feel the effect of the quasi-Lidov cycle, not all of them actually enter the so-called liberation zone, where we get these big swings in the eccentricity and inclination, and hence big changes in the orbit. And here you can see all the near-Earth and Earth-crossing comets. And we see that only a handful of them actually enter the liberation zone. So all the ones that are outside don't have the capacity to produce that same variety of showers. And we wanted to quantify this. So quantify how many unique meteor shower producing encounters our batch of comets can produce. And to do so, I used an impact code by Peter Pokorny, and which essentially computes how often a projectile orbit, so like a comet, intersects with a target orbit, which is the Earth in our case. And the result is 476 unique Earth-crossing configurations. So 476 unique opportunities when a comet's path crosses the Earth's orbit, and therefore we could be able to see showers. But this leads us to our next question. How do those meteoroid streams even stay coherent long enough to realize all these intersections? And because if a stream fades away before a comet can complete its full cycle, we wouldn't even be able to see all these predicted showers. So to be able to answer this question, I have simulated the orbital evolution of the nearest comets and computed the secular period, which peaks around 100,000 years. So then this number can be compared to the typical lifetimes of meteoroid streams. And those meteoroid stream decoherence times have recently been computed by Schober et al. As a function of eccentricity and semi-major axis for 100 fictitious streams. And here are the maps for different inclinations. And once again, if we overlay our mean orbital elements of our showers, we see that most of them fall into the red to green zone, meaning typical meteoroid stream times of 5,000 to 50,000 years. And recall that the secular period of near-Earth comets was around 100,000 years. So a lot of the meteoroid streams would fade away before its parent comet could complete its full secular cycle, including quasi and precession cycles, etc. So we would actually not be able to see all those 400 predicted showers. So where did the rest of the showers come from? And to be able to answer this question, we're turning into asteroids now, especially the ones that are near Earth and on Earth-crossing orbits, the ones that are hydrated and active physically, to see if they can account for the numerous meteor showers. And this is very much work in progress, so stay tuned for further results. Thank you.
Thank you, Aisha. And sorry again for the technical problems. I guess we have time for one question so that we don't get too late with because we have one more talk and then the coffee break. I already see faces that they are craving for coffee. So, Yura.
Maybe quick one to leave the time also for second one. Actually, very nice talk. Did you also account also for a helitype cometary orbits, because you didn't mention in the Earth cross helitype?
Yes, so well, I said that the nearest comets and the ones that are Earth crossing can be of any type. Just in this case, I'm taking the MOID, the minimum orbital intersection distance, to be very small, 0.05, but it can be a comet on any sort of orbit, a long period helitype. So yes, I just didn't specify which ones. Yes.
Okay, so thank you again, Aisha. And now we welcome